false? Linear algebra makes an epic comeback in chapter 3.
You betcha.
Yep. We'll have lots of linear algebra. Part of today's lesson is a little review of the stuff that you'll need to know from linear if you weren't here in the fall. If you haven't had it yet. Okay, this system, x dot equals ax plus by and y dot equals cx plus dy. Remember, x dot and y dot just mean dx dt and dy dt, time derivatives. They're called what kind of a system? Linear.
Makes sense now.
Checked it off.
If we want to write that system using vectors and matrices, a couple of different things I'll accept. So we'll do it a couple different ways.
Our coefficient matrix A is equal to A.
Yeah. So you could use your vectors. Just write out all your vectors. So you've got x dot y dot is your vector of derivatives. Your coefficient matrix is A, B, C, D, and then you multiply that times your x and y, right? Or you could have defined each of these things by naming it, right, and then writing something to the effect of y dot with an arrow or a bold, right, and that encompasses the x dot y dot. You could have named this matrix A, and then this would be y to represent the x, y together. Either of those would be fine. Okay, so
I would do other things for last.
So we're starting our new packet today. We're going to start chapter 3. The first part of your final project that I just handed out is based on Euler's method. So I'm going to have you program Euler's method using Excel. It's fairly straightforward if you've ever done anything with Excel. So that part you can do like right now and get that done. The second part of the final project of 3 total parts. The second part is mostly based on chapter 3. Okay. So I decided to give it to you today so that as we work through chapter 3, you can kind of work through the second part of the project. And then the last part of the project is based mostly on chapter 5. So one section of chapter 5 that we're doing. So you probably won't be able to do that for a while, but you can at least do part 1 and start part 2 now. And then you have lots of time at the end of the semester after we cover 5.1 to finish the third part. And it's due the day our final exam is scheduled for. So May 18th. You can submit it, I said through Moodle. I'll have a button there if you want to submit it electronically through Moodle, or you can email it to me, or you can just put it under my office door. I'll get it somehow. Yeah, I also figured if I give it to you now, I'll be here for more availability for questions as you work through it.
I'm sorry, you said Ian has solutions, right?
Yeah. Yep, Ian and Sandy and Bob will all have worked through the whole project by the end of the semester, so they'll be available to help you. Okay, so first we're going to talk a little bit about linear algebra. So we just have a little mini linear algebra lesson. So this will be pretty familiar if you took linear algebra. If it's not, this is like just the super basics. So really fast lesson. So this is going to be helpful when we're studying linear systems, which is the topic of chapter 3. So a vector is just a list of numbers. Usually you write it vertically, but not always. Sometimes you write it horizontally, like a point x comma y versus vertically x, y. A matrix is just an array of numbers that are made up of column vectors. And the size of a matrix is described by giving rows and then columns, number of rows, number of columns. So this matrix here is a 3 by 2 matrix because it has 3 rows, 2 columns. So we're going to need to be able to multiply matrices. To multiply 2 matrices, the number of columns in the first has to equal the number of rows in the second, and the product will have the number of rows from the first and the number of columns from the second. That sounds confusing, but when you write it out, like if I want to multiply a 3 by 2 by a 2 by 4, basically the inner dimensions have to match in order for these to be possible to multiply, and the result is the outer dimensions. Okay, so these can be multiplied because the inner dimensions are both 2, they match. The result is a 3 by 4 matrix. So when you're multiplying two matrices, you take the dot product of each row in the first matrix with each column in the second. Okay. So first of all, I like to write out what the dimension is going to look like before I start multiplying. By the way, your TI can do this, but I just, in the event that we're multiplying, some of these things are variables, you need to be able to do this by hand also. So this matrix here is a 3 by 2. This matrix that I'm multiplying by is a 2 by 2. The inner dimensions match, they're both 2's. The outer dimension is 3 by 2. So that's what my answer is going to be. It's going to have 3 rows and 2 columns. Okay, so my answer has 3 rows, 1, 2, 3, 2 columns. So I kind of just like outline what the answer is going to look like before I start doing any calculations. All right, finally you do the dot product of each row times each column. So when I multiply, or dot product, the first row times the first column, that goes in row 1, column 1 of the answer. So this is going to be 1 times 1 plus negative 2 times 3. Right, the dot product means multiply corresponding entries and then add them together. I always picture taking this row that I'm multiplying by, and like I pick it up off the board, rotate it 90 degrees, lay it on top of the column I'm multiplying by, multiply the things that line up, and then add them together. All right, so that's row 1 times column 1. When I multiply row 1 times column 2, that goes in row 1, column 2 of the answer matrix. So I have 1 times 2 plus negative 2 times 4. All right, so I have now exhausted row 1 from my first matrix, so I move on to row 2. Then I do row 2 times column 1 and row 2 times column 2. That gives me row 2, column 1 and row 2, column 2 of the answer. So I'm going to have 1 times 1 plus 5 times 3 is 16. 1 times 2 is 2 plus 5 times 4, 20, so 22. And then that's 1 plus 21 is 22, and 2 plus 28 is 30. Got it? Make sense? All right, this one came out to 2 minus 8, so this one's negative 6. And then this one is 1 plus negative 6 is negative 5. So here's another little thing. In linear algebra, we always, for matrices, use these square brackets for a matrix or for a vector. Your textbook often uses round brackets. It's the exact same thing. Just don't let it confuse you. I'll probably go back and forth.
Try and mix and match.
Yeah, you can mix and match.
So round on one side, square on the other side.
We don't do that. Okay, so matrices are typically named with a capital letter. Vectors are usually named with either a bold letter or a letter with a little arrow on top of it. Again, with the bold and the arrow, I'll use them interchangeably. So for example, I might name this matrix capital A. I might name the vector xy the bold x. All right, so a linear system. So that's moving on from our linear algebra lesson here. A linear system is a system that looks like x prime equals ax plus by, y prime equals cx plus dy. We can write this linear system much more efficiently using vector and matrix notation. So A is going to be all the coefficients on the x's and the y's, right? So my A matrix is A, B, C, D. It's called the coefficient matrix. The bold y is going to be the column vector of dependent variables x and y. And let's look at what happens when I multiply a times y, right? So I've got a, b, c, d times the column vector x, y. And then I'm going to use the exact same process I just showed you for how to multiply. The result of this is 2 by 2. This vector is 2 by 1, so what's my result going to be? 2 by 1, 2 rows, 1 column. So it's just going to look something like that. And then you take the first row times the first column and do the dot product. So you have ax plus by. And then the second row times the column, and you get cx plus dy. Right? So when you multiply your coefficient matrix times your column vector of dependent variables, you end up with the right-hand side of your differential equation of your system, ax plus by and cx plus dy. And then if this bold y, if that is a vector of x, y, your dependent variables, then bold y prime is just x prime, y prime. So we can finally write this system as y prime equals a times y, or where a is the coefficient matrix and y is the vector x, y. So we're going to be doing lots of practice of going back and forth, writing these things as two equations versus a matrix equation.
So why is it a y instead of a x?
Just author's choice. Yep. So the question was, why did we call this xy vector, why did we call it y as opposed to
Y.
x, right? You can call it either. It was just the author's decision. I think it's because typically when you only have one differential equation, you use y as your dependent variable. So now we're kind of squishing two equations into one vector, so we stuck with y. All right, so the harmonic oscillator that we talked about in Chapter 2, and by the way, you were unable to solve in the test because I messed that up. I put a question that you couldn't finish, so everyone will get credit for that question. It was number 6. Yeah. I meant to tell you that earlier.
Number 6. I don't remember what that was.
It was a second order differential equation, like something like this, but you had numbers for m, b, and k, and it was solve the initial value problem.
Oh, thank God.
Yeah. We'll learn how to solve that soon.
I thought I did that pretty good.
I just forgot about the initial value.
Yeah.
Five, zero.
What I meant was you just find two particular solutions, which is what we have done. You can't solve an initial value problem with it yet.
Okay.
Yeah.
Oh, I got it.
So just for example, this is an example where a system could be useful, right? You can take the harmonic oscillator, you can rewrite it as a system, and just for practice, let's rewrite this using vector and matrix notation. Right? So we're going to write this as a vector equation. I mean a matrix equation. So I have y prime, v prime equals my coefficient matrix, which is what? What is my coefficient matrix for the first row?
0, 1.
0, 1, yeah, because I'm going y, v is my order here. So I have 0, 1. And then for my second equation, my matrix, my coefficients are negative k over m and negative b over m. And that should get multiplied times what? yv. And you can just double check if you're not sure, or if you should have done 0, 1 or 1, 0, just multiply it, right? You take your 0, 1, multiply by yv, you get 0y plus 1v, and that is what we were supposed to get over here. 1v. Okay, so that's one thing you can model with a linear system is the harmonic oscillator. But we can model all kinds of things besides a mass on a spring. So for example, love affairs. And this is what you're going to be doing in your project, in part 2 of your project. Looking at various Romeo and Juliet situations here.
No, and that wasn't stupid. That was my project.
All right. So let's do an example here. So Romeo's in love with Juliet, but in our version of this story, Juliet is fickle. The more Romeo loves her, the more she wants to run away and hide. She's like claustrophobic. Right? But when Romeo gets discouraged and backs off, Juliet begins to find him strangely attractive again. Romeo, on the other hand, tends to echo her, right? When she loves him, he warms up and loves her more, and when she grows cold, and then he grows cold when she hates him. Sorry, he grows cold when she hates him, yeah. All right, so R of T is going to represent Romeo's love and hate for Juliet in time T. J of T is going to represent Juliet's love/hate for Romeo at time T. So we're going to just use positive values of R and J means love, and negative values means hate. Okay? So I want to write a system of differential equations that might model this situation. Okay. So if I want an R dot and a J dot, right? So how does Romeo's love change? How does Juliet's feelings change in response to the other person's feelings? So let's see, in the description we start talking about Juliet first, right? So it says the more Romeo loves her, the more Juliet wants to run away and hide. And vice versa, right? When Romeo gets discouraged and leaves her alone, she likes him again, right? So this is J dot. This is how Juliet's feelings change. She responds to Romeo's current feelings in the opposite way, right? So
As an inverse.
So it's going to be negative. Yeah, so let's just call this negative R, right? So she just has like her feelings change in the opposite way that Romeo's feelings currently are. All right, Romeo, on the other hand, echoes her, right? When she loves him, he warms up. When she hates him, he grows cold. So just J, yeah. So Romeo's feelings change in proportion to Juliet's feelings. Okay, and I just chose the most easy coefficients here. We just chose the easiest coefficients of 1 and -1. There's nothing in this description that tells you what the coefficients are. I just picked easy ones. Right, so first let's write this for practice as a matrix equation. So I've got R dot and J dot. What's my coefficient? What are my coefficients here?
0, 1, 1,
0, 1,
negative 1, 0.
-1, 0. Great. And that gets multiplied by R.
That's a standard matrix.
Almost the identity matrix. Okay, so again, we chose the simplest possible values for the coefficients there. I used a computer program, which is what I'm going to have you learn how to do in your project, to create a direction field and a phase portrait for this system. Okay, so this is the RJ plane. So again, you can't really see time in here. Time is like how you draw these circles, watching them be drawn in real time. But this is Romeo's feelings versus Juliet's feelings. So what does this say about their relationship? What does this picture tell us about them? It's cyclical, yeah.
Periodic is something over time.
Yeah. If I was going to graph Romeo's feelings over time, it would definitely be periodic, sinusoidal. Yeah.
So when it's higher in the J and the R, it means it's more in love.
Yeah. So up here in the upper right quadrant, this would be their mutual love, right? They're in love with each other up here, right? What's happening in the lower left quadrant?
Domestic abuse.
They hate each other. Yep.
Domestic abuse is when he loves her.
All right. And then the other two quadrants are like the really sad cases, right? Where one person loves the other, but the other one hates them, right? So in this case, the lower right, Romeo loves Juliet, but Juliet hates Romeo, right? Romeo
This is a typical middle school relationship.
loves Juliet, Juliet
But usually people
hates
would
Romeo,
just go with this.
and then vice versa up here, right?
Like this.
Romeo hates Juliet,
There was no like. As soon as I'm
and then Juliet
no,
loves Romeo. Right, because here we're in negative R's and positive J's. So Juliet is in love, but Romeo is Juliet. So if I was going to describe their relationship, I would say this is a cyclical, like on again, off again,
Yeah, at some point it's different.
off again.
Point together, yeah.
I don't know, tumultuous relationship, right? I don't know how to spell that.
You got it.
And those circles, those are special conditions, right?
Yeah, those just are for various initial conditions. Yeah. There's one fixed point here, right?
Yeah.
If they start out mutually indifferent to each other, they'll stay that way forever.
So what you're saying is love is a lie.
I like consistency, so.
He's 50 at that point.
So your project is kind of fun because you get to characterize the romantic styles of various Romeo and Juliet scenarios. So in this case, Juliet was fickle because she responds in the opposite way to Romeo's feelings, but there's lots of different situations we can describe using a linear system here. All right, so that's it for the demo. You can work through some of your activities here, and I will help.